So a theme that's been emerging in this learning module is that it's getting harder and harder to accurately depict the complex phenomena surrounding molecules. We need to have a deeper ways of looking at these molecules, and a really a nice deep way of looking at molecules that can also be done using some shortcuts on paper without complicated mathematics involves molecular orbital theory. So molecular orbital theory is actually grounded in some pretty complicated mathematical equations, but we can take some shortcuts when thinking about some patterns to start to make sense of what's happening and what the results of molecular orbital theory can reveal to us. This provides deeper insights into molecules and gets us better and better at describing these molecules and ultimately understanding chemistry. So this is a deeper way of thinking about covalent bonding. Okay, so to do this, we need to go back to the orbital, just to remind ourselves of what an orbital actually is when we're using them. So orbitals are, or sort of represent, three-dimensional space that an electron can exist in. So, and by an electron, it could be an electron or a pair of electrons, two electrons within an orbital, right? Okay, so we started by looking at atomic orbitals. And atomic orbitals are orbitals that can hold, hold an atom's electrons. Okay, but now when atoms form covalent bonds, they actually make molecules, right? And the valence electrons then actually exist in molecular orbitals. So these are different from atomic orbitals and they should be labeled as such. So these are molecular orbitals. And I've mentioned this before, at least in Organic 1. So again, these are the orbitals that hold valence electrons in molecules. So they result when molecules are formed. Which result when covalent bonds are involved, right? Because molecules result from the covalent bonding as opposed to salts, which generally result from ionic bonds. Okay, so a nice starter example when looking at molecular orbitals is to think about H dot reacting with itself to make H2. I'm going to show the bond as either a Lewis dot structure or a line between two H atoms. So we have two one electron systems. So we could consider those as being in s orbitals. S orbitals are nice and easy to consider because they're spherical. So these are the 1s atomic orbitals. Now, when H2 is formed, we see overlap of the 1s orbitals, and we could consider the overlap like this. And though incorrect, we could consider the electrons as sort of being in the space in the head-to-head overlap. So this is the sigma bond that results from head-to-head overlap. Now I realize these are spherical, so they don't have heads in the normal sense. Head-to-head overlap of, and these are 1s orbitals because it's hydrogen, so we just put all the electrons in the 1s orbital. I never really liked this depiction. It's kind of cute because it makes the overlapping orbitals into a Venn diagram, right, where you can show the electrons positioned. But I mean, in reality, the electrons can exist anywhere within the combination of these two atomic orbitals. And a better way to depict that, as opposed to thinking about like a summative or a linear combination of these two atomic orbitals, is to redraw the orbital as a single molecular orbital that the electrons can exist in. Alternative molecular orbital. So this molecular orbital results when H2 is formed. So in our 1H atoms, we would say those technically don't have molecular orbitals, they have atomic orbitals. But when the molecule forms, the covalent bonding electrons are housed inside molecular orbitals. So when we want to think about the shape of this molecular orbital, we can use some complicated mathematics to actually determine the shape, the overall shape of this molecular orbital. What we might want to do instead is think about some rules, because at this point in the game, we're trying to do as much organic chemistry on paper. So there are some rules to help us get there, some rules for forming molecular orbitals that we can apply to paper that emerge from complicated mathematics, ultimately grounded in quantum mechanics. So rules for forming molecular orbitals. Okay, so these are the things that result from the complicated mathematics. And as a result, some of them might not be super intuitive, and we might have to just commit some of these to memory to move forward, but we'll get there. So the first rule is that the number of orbitals you start with must equal the number of orbitals you end with. Okay. And the end with orbitals, these are going to be our resulting MOs, where MO stands for molecular orbital. Okay. Now, this is important. And so the number of orbitals that we start with, these are typically AOs, or atomic orbitals. So in the first example, we had our two 1s electrons resulting in a molecular orbital that was oval shaped and was able to hold both of the electrons. So this is called our bonding molecular orbital. Now, the thing that also results is an empty molecular orbital, which is our anti-bonding molecular orbital. So we start with two AOs, or two atomic orbitals, and we get two MOs after we add those together. Okay, just one of them is empty, and it's considered to be an anti-bonding orbital. Okay. So the orbitals, the molecular orbitals, I'm going to write that out just so we'll use the abbreviations in the picture. But the molecular orbitals that result can be bonding molecular orbitals. And the bonding molecular orbitals are most stable or lowest in energy. To They can either be bonding or anti-bonding molecular orbitals. And these are the least stable or highest in energy. Okay. And then 3, we could have non-bonding molecular orbitals. And this would be where you kind of put your lone pairs or electrons not involved in bonding. So we're always going to see examples of 1 and 2, and it's just sort of occasionally that we see opportunities for non-bonding electrons. Okay. The takeaway here, though, is for each bonding orbital, there's an anti-bonding molecular orbital. One anti-bonding molecular orbital. Okay, so that's kind of the number and types of orbitals. Whenever you need a bonding orbital, you must also generate an anti-bonding orbital. So there could be, there's often the case that we have multiple bonding orbitals, the same number of anti-bonding orbitals, and on occasion, non-bonding orbitals. So non-bonding orbitals are in between or sort of neutral stability. This is where you usually put the electrons that are kind of coming along for the ride. Okay, so with this information, we can actually determine what's called the bond order. It's not exactly the same, but if you thought about this as the, so I say it's similar to the number of bonds between 2 elements. If you thought about it that way, it's okay. Okay, so the bond order is equal to the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. I'm running out of space. I'm just going to move this down. You don't have to redraw it. In anti-bonding orbitals, and then you divide that by 2. Okay, so let's look at an example of this. So H2 has a bond order of 1. Well, we could have guessed that if we draw H2, we show one line between the 2 H atoms. But if we try to calculate it, what I said before was that we had 2 electrons in bonding orbitals and none in the anti-bonding molecular orbitals. Okay, so if we take 2 minus 0 divided by 2, that's equal to the bond order. Because it's the number of the electrons. It's not like the number of bonds or the number of orbitals. If it was the number of orbitals, it'd always equal 0, right? So we have 2 in the bonding minus 0 in the anti-bonding divided by 2. That gives us 2 divided by 2, which is 1. So we can kind of quantify the number of bonds that are between 2 elements. This is helpful because sometimes we can achieve bond orders of like 1.5, partial bonds. And so this is a little bit more correct than just having the number of lines tell you how many bonds are between two elements. Okay, so what about bond order and non-bonding orbitals? Okay, so what about bond order and non-bonding molecular orbitals? Well, it turns out that non-bonding orbitals do not encourage or discourage bonding. Non-bonding orbitals do not encourage or discourage bonding. And as a result, they do not change the bond order. And they're not included in our little equation. Okay. So when do you see non-bonding molecular orbitals? These are often seen if you have an odd number of atomic orbitals. Used to form your molecular orbitals. And that happens quite a bit when we sort of are able to delocalize charge somewhat. Okay, so what we can do is we can start to construct energy diagrams for these systems. And so I feel like this is a good start. So in the next lecture, we'll look at energy diagrams for molecular orbital pictures. So we'll stop here with this lecture as sort of an introduction to molecular orbital theory. Pick up with this next time. So until then, I'll see you next time.